Good morning. I'm Barry Wise of Eigenvector Research, and this is everything you need to know about pre-processing in PLS Toolbox and Solo. And today our main presenter will be somebody who needs no introduction, especially if you believe those scientific citation indexes, right, Rasmus?
That's true. Yeah.
Yeah. So Rasmus Bro is gonna take over today. And I'll be doing just a little bit here as we go along. And just a couple of notes about how we do this. This webinar is being recorded, and we'll post it on the webinars section of our website. This is actually number 18, I think, in the series that we've been doing, and there are a few addendums too. So there's over 20 videos that are posted there that span all sorts of topics about how to do various stuff in our software and how various methods work. So that's a pretty good treasure trove of information. So today I'm going to act as the moderator unless one of the other Eigen guys butts in, but they will probably speak up at some point or another. We've got quite a few of our crew actually here today. I think that includes Neil, Lyle, Bob, Sean, Scott is who all I've seen so far.
And Manny.
And Manny, is Manny here too?
He is.
Okay, good. And please keep yourself muted. We generally don't use video also. Rasmus is using his, I see a little bit there, just so you can see he's actually live. And please, if you have questions, put them in the chat. And then the questions will be relayed from the moderator to the speaker, or sometimes they get answered directly in the chat. But we find that actually works pretty well if you do that. And we will try to get to your questions. And with that, I'm going to say, take it away, Rasmus. And then I have to stop sharing and pass the ball to Rasmus.
Yep.
So let me find him in the list. Are you under R for Rasmus? There you are.
I have no idea. Yeah, it should be. Yeah. Yeah.
Yeah. Okay. So I have to change your role to presenter.
Q. Here we are.
And there you go.
Thank you. Let me just turn off my video. Now seeing that I exist. Okay, thank you very much. So as Barry said, my name is Rasmus Bro. I work at the University of Copenhagen in Denmark, where we have a chemometric group, a pretty big one in a food department. But I also work a lot with the Eigenvector guys. So I'm a little bit yeah, you can't trust me completely. But anyway, I'm a fond user of the toolbox since I guess 1994, where I could download it for free on Gopher. It was before HTTP, and I've used it throughout all the years. So today we're going to talk about pre-processing, and that's one of the nice things in PLS Toolbox and Solo, is that you really have access to a lot of different types of pre-processing. And I'm going to go through some of them, but not all of them. If you have questions or questions about specific ones, just let me know, and we'll see what we can do.
Hey, Rasmus, just so you know that icon that says customize your view by dragging one or more videos to the stage is still up there.
On mine?
Well, I see it on yours.
This is funny. Before I was the only one seeing it, and now you are.
It was on mine. Okay, good. Jeez.
Okay, it's complicated.
It
all
is.
this IT stuff. Okay. Now, before I talk about pre-processing, it might be worth considering why you want to pre-process your data. Actually, in the early days of you can say the current hype of deep learning, artificial intelligence, machine learning, in the beginning of that hype, not so many years ago, people sort of had the idea that we can do really complex neural networks, and then we don't need to worry about preprocessing. And while that is to some extent true sometimes, there's also a realization that, okay, there's no benefit of making things more difficult. It doesn't actually benefit your model. If you can make your data more appropriate for your purpose, it's probably a good idea, of course. So some of the main reasons for preprocessing, well, I guess one is to linearize your data, like pH, absorbance, and things like that. Those are kind of, I mean, we know that the concentration is linearly related to absorbance, so why not use absorbance as a unit rather than transmittance or whatever. So linearizing your data in general makes it easier for your model to actually model the data. And I guess the other big thing is just to remove bad stuff, like if you have scattering in NIR, stuff like that. If you can remove information that is clearly not of interest for whatever you're trying to do, that is probably a good idea. Well, that is a good idea. And I guess for me, that's the main reasons for doing preprocessing. So kind of overall, the idea is you want to simplify your modeling, because that will always be beneficial. It's easier to interpret your model. It's easier to understand what it's doing. It's going to be more robust in a statistical sense, etc. So these are at least some of the main reasons. I'm sure there could be other reasons as well. So let's take a look at preprocessing in PLS Toolbox. So if we go from the browse window, this is the window you will see normally in Solo if you're using that version of PLS Toolbox. If you're using PLS Toolbox within MATLAB, you may start in some analysis window like PCA. And let me just start in PCA. I already have loaded a bit of data into my workspace, and I'm going to use these data sets for showing different things. So let me start by loading up a data set. It's a spectral data set, 40 samples and 900 variables. And it's always, and we always preach that you should look at your data, and that is definitely a good idea. So once I have loaded my data here, I can say plot data, and I can see different things. The default is that I get the mean of my variables, in this case of my spectra. I'm going to change that to the actual data. And so this is it's a this NIR, a spectral data set of some beer samples. And the two main types of preprocessing that we normally worry about, well, you can find them here in PLS Toolbox. That would be mean centering and auto-scaling. Let's just start with mean centering these data. So now if I mouse over, you can see that this little tip appears and shows me that I have mean centered my data. And it's a really good idea, and some people sometimes forget that, to not just look at your data, your actual data, but also take a look at your preprocessed data. And you can do that, for example, here. You can say plot the preprocessed data. And what you will see here is, well, this is the mean. That's not very interesting because the data have been centered, so the mean is approximately 0. But this is my actual centered data. And I hope you can see the difference. And actually the centered data, that's what we're going to use when we model the data. And you can see that you can somehow be deceived a little bit and think, oh, this is an important area. Well, okay, if you're spectroscopically inclined, you can see that it's very noisy. But anyway, it seems like there are big values. But actually, on the preprocessed data, we get a much clearer view of actually what is going to be presented to our modeling tools, PCA or PLS or what have you. So it is extremely useful to always take a look at your pre-processed data, not just your raw data. And also, I want to highlight some of the things that you can do, some simple things you can color by. So when I'm looking at my data here, actually, we're interested in predicting something called extract. It's a quality parameter for beer, not important here. And I have that available. Extract, here we are. So instead of having just these random colors, I can color my spectra by the Y value that I might be interested in predicting. And I can see here very clearly that the visual area is seems not to be very correlated with my Y parameter. I put a scale here. But if you look in this area here, zoom in a little bit, you can see that this is definitely interesting. It almost looks like we can read off the Y values from these two little peaks here, or three little peaks here. So plotting by different things can be very useful. This thing, I hope you can see my cursor when I'm moving it, otherwise complain. But this little thing here is just a detector shift. It's not really interesting. Okay, so this is mean centering. That's one of the most basic things. This is one of the most basic types of pre-processing, and the other basic one would be auto-scaling. And I don't know if you can imagine what this data set is going to look like if we auto-scale it, but let me try. And let me say plot the pre-processed data. And again, we get the mean, but I want the actual data. And if you compare, you can see that that looks relatively terrible because in the high end here, you clearly have just noise going on. And auto-scaling the noise in this case is going to blow up the noise, and we really don't want that. Also, this type of data is not something you would normally apply auto-scaling to. But you can see that it blows up the noise enormously. So if we want to do auto-scaling, we should sort of make sure that our data is relevant. I mean, all the variables are relevant. Now we can actually remedy this a little bit. Let me show you the kind of the pre-processing bonanza is in this one. And if instead of choosing between mean centering, auto-scaling, and none, if we go here, we actually get a list of all the available types of pre-processing here. And you can see that there's a lot of different things that we can do here. I'm going to go through some of them, not all of them. But here you can see, for example, here you can see that we have auto-scaling chosen. And one very nice thing here, and I cannot stress that enough, is this little button down here called show. So if you press that one, you get a kind of a simplified plot. I mean, you don't have all the functionality that you normally have in plots, but you get a view on the left of your raw data and on the right of your pre-processed data. So if I remove auto-scaling, I don't have any pre-processing chosen, and I get the raw data back. Let me go down here and find auto-scaling, apply it again. Now, some types of pre-processing, like auto-scaling, will actually have settings that you can modify.
Hey, Rasmus,
So, yes?
can I interrupt you for just a second? So we had a question on the
Absolutely.
chat about when should I use mean center or auto scale? Is there any rules? So if you
Yes.
could just kind of hit that.
Yeah, absolutely. So I'm from Europe, so apologies, but imagine I measure the height of persons, and it's going to be in meters, sorry, like this. And then later on, I take a second type of instrument for measuring the height, but this time I'm going to measure in centimeters. So basically I did the same type of measurement twice, but using different units. Now, if I do PCA on this little data set, it's going to say that this is just 0, because in PCA and in most of the methods that we talk about in data analysis, the models will focus on magnitude, which really just means the size of the numbers. In reality, it means the variance or something like that, but it really is big numbers are important, small numbers are unimportant. So if I input the data like this, I explicitly tell the PCA or whatever, X1 you shouldn't focus on. X2, that one is really nice. So what you can see here is that we really need to do autoscaling, because what autoscaling does is that it makes the variance of X1 exactly the same as the variance of X2. So if you generalize that, the thing is that every time you have discrete variables, you would do autoscaling. Now, there will always be exceptions, so understanding the impact gives you a sort of added flexibility. But sort of one rule of thumb would be discrete variables. Another rule of thumb would be if you were not in chemistry, do autoscaling. Because the thing is, in chemistry, we often measure continuous data of some sort, like a spectrum. If you look at my green data set here, you could see that the two columns, the scale was not comparable of the different columns. But if I measure spectral data like this, then actually the scale of this column is comparable to the scale of that column and is comparable to the scale of that column. Here I have 0 absorbance, meaning no chemistry. Here I have high absorbance, meaning lots of chemistry. So for that type of data, we would not do scaling. And if you want to simplify it, the rule of thumb would be continuous data. So also time series, yeah, stuff like that. There's more to it, but conceptually, this is it. You have to think about what is information in my data. And here, actually, in the spectral data set, small values means that you have less information. Okay, I hope that helps.
Yeah, I think that's good, Rasmus.
Good. Okay. So what I wanted to show you here was that, okay, we did this auto-scaling, and it turns out that's not so smart because we blow up the noise here. Now, many of these pre-processing methods actually have settings, and they can be intimidating at times, but there's typically help. So you can click the help and get an idea about what things mean. So for example, the problem here is that when the variance is very small, autoscaling will scale up because we're going to divide by a small number. So we're scaling down big variance, but we're scaling up small variance. So we could add a threshold and say, okay, it's fine in autoscaling that you divide each column by the standard deviation, but let me put a threshold. Let's say 0.1. I don't know how that will work, but it's absorbance. So something like that. If the variance is below 0.1, let's just do 0.1. And it actually works, kind of. You see, we're not blowing up the noise quite as much, but we're still kind of equalizing here a little bit. Not as well as before, but it's kind of a compromise. So you may want to play around with these things. As I said, I wouldn't do auto-scaling on these data. So anyway, but it's just to show that you have these added features here for some of the types of pre-processing that can be very useful. Okay. Let me load up another data set to show some other types of scaling. Let me load up a chromatographic data set. And it's a tick data set. So if you're not familiar with chromatographic data, no worries. Let me just explain. Oops. Now I can't find my plot control, but if I have the plot the window with the plot in, I can just go here and say find controls. And I get them back. That's good. So this is a data set. This is a chromatographic data set. So we have peaks coming out at different points in time. I can see I lost the scale here, but this would be 10, 20 minutes or something. Now what you can see is that some peaks are very big. Some peaks are very small. There's orders of magnitude difference. And then also, I've been so stupid when I did my measurement that I also measure nothing. This is just baseline. There's no information here. So basically, depending on what kind of chromatography, you may have mainly nothing. That means time points that don't contain any chemical information. So I don't know if you can imagine what would happen if I would do auto-scaling on this data set. It would be very similar to what we saw on the beer data. Let's see now. You can see that looks terrible. And that's a pity, because if I don't do some kind of scaling here and do a PCA, it's going to focus on the big peaks and it's going to say all the small ones are not really nice. And that's a pity. Now, the nice thing is that we have different types of variations of scaling. And there's in particular two that are very popular. One is called Pareto scaling, and the other one is called Poisson scaling. Now let me remove the auto scaling here. And this is the Pareto scaling is similar to auto scaling, but instead of dividing by the standard deviation, it's dividing by the square root of the standard deviation. And you will see that that little difference has a big impact if we try and do that. You can see that I'm not blowing up the noise like we were before. And even if it's not perfect, I've still equalized the size of the different peaks significantly. Not perfectly, but I've made them less different. In the Poisson scaling, instead of dividing by the spread, how much the peaks are varying, we are dividing by the mean, what's the average signal. It's kind of similar, but a slightly different flavor. Let me try and do that one here. That actually looks nicer to me. But anyway, both of them did sort of a much better job than auto-scaling did. And actually, we can even do it twice. People don't do that much, but there's nothing wrong or illegal in doing it several times. You can also do it 5 times if you want to. People normally don't do that. People would normally do it once. And then, of course, once you're done, you would also do mean centering. But often when I sit and play around with pre-processing, sort of interactively like we do here, I'm going to remove the mean centering because I want to see the effect sort of in more terms of raw data. So I will only add the mean centering in the very end. I want to see this. It makes more chemical sense to look at the data like this than after mean centering. I do want the mean centering in the end, but for analyzing and understanding what I'm doing, I prefer to work without the mean centering. Also notice.
Let me just emphasize that. I mean, this tool is really handy for looking at it as you add pre-processing steps, and especially if you have multiple steps. In some instances, we might wind up with 3 or 4. You know, look at it after the first one, after the first 2, after the first 3, and see how, if it's going the direction you think it ought to be going.
Right. And just another thing, if you're kind of doing, let's say, simple pre-processing, that means centering or scaling, centering and or scaling. It doesn't really matter in what order, because mathematically you can show that these two particular types of pre-processing, they are sort of independent of each other. But in general, order matters. If I move mean centering up, that means I'm doing mean centering and then Poisson. That's gonna go wrong, I guess. Well, it's different anyway, because now I'm dividing with the square root of something that is already, the mean is already 0. So that can go completely wrong. One classical example would be MSC after mean centering, multiplicative signal correction. We'll talk more about that. Okay, but anyway, what I wanted to say is that there are alternatives to the traditional autoscaling. These Poisson and Pareto are very popular in omics, not just for data like this, but for NMR data, MS data, and other types of data where there's orders of magnitude difference between your variables, and where that difference doesn't matter. I mean, if this is, and it is, aroma, this one may, the flavor of this one may be way more intense than the flavor of this one. The area doesn't tell us the flavor intensity. So if I'm interested in flavor, I want all peaks. I don't want the big peaks in particular. Okay, now since we have these chromatographic data, let me just show you one of the problems you often have in chromatographic data is that you have retention time shifts. If you look at this particular peak here, that should really come out at the same time, but it doesn't, and that's pretty standard. Well, it can depend on many different things, but over time, your peaks will vary a little bit, and that sort of destroys Beer's law, and it can complicate the data analysis depending on how you approach the data. Well, if we go up here, there's actually tools for handling that. There are different tools. One very popular one is one called COW, correlation optimized warping. Let me just zoom out again. This, okay. And let me now add COW. And there's some parameters you have to choose. I don't have time to go into all of these, but basically you have to determine how many time points do you want to try and align. So the algorithm will actually take small segments and align them. So it goes from left to right, and it takes small segments and it tries to adjust the time axis. And the slack, the higher the slack, the more you can flex those segments, the more you can move them to the left and right. I mean, physically, it means you can move them 5 points to the left and right. And what I want to show you here is that this is a very flexible setting. So I want to show you that this would probably go wrong. Let's see. So now I'm applying correlation optimized warping. And we take a look at the data. And yeah, okay, that's good. So it actually did go wrong, which is what I wanted. You see, it sort of aligned most of these much better than here, but then one of them sort of slipped away for some reason. And also here, that would be the same thing. That's actually one peak that has been split up. This is an intrinsic problem in COW. You have to find the compromise between flexibility and sort of maintenance of the basic features. Also like area, you can align perfectly, but destroy the area completely. Now there are actually tools also in the toolbox if you have MATLAB to sort of search through the settings. But what we usually do is that we sit and play around with settings. Like I think if I do less time segments, so longer ones, it's going to be constrained enough that it's not going to go berserk, and it's going to align pretty fine. Of course, you should check all your peaks, especially the smaller ones, and you may actually want to scale up those before you align, because then it's going to focus more on the smaller ones, etc. COW is a very standard tool for aligning data, and a very powerful tool. And powerful also means that you can do crazy things, so you have to be careful when you do that. Okay, now let me load up a very simple data set and do a PLS model. I have one X variable and I have, oops, one Y variable. Here we are. So I'm going to change now to a PLS model, and I will show you the data. It's just one variable, so it's almost silly. What? Let me see. That's fine. It's fine. We build a model. That's going to be a one-component model since I only have one variable. What I want to show you here is the predictions. And we get the default plot, but I mainly want to show you the predictions. So the green line is the identity. That's where all the points should be. Now you can see here that we clearly have some kind of nonlinearity. This is a very simple data set, but you can see that we have a clear nonlinearity. And I just want to show you that we can sometimes handle that by transforming, well, either X or Y. So let me go in and take a look at, oops, X. So you see here, we can actually do basic sort of transformations. In this case, maybe we can do just a square of X, so X to the power of 2. And we can see if that will do the trick. Let me try and do that. So I have to define that C is 2. And it's going to be on all the variables. Well, I have one, so that's kind of boring. And I want that before my auto-scaling. I want the raw data, otherwise it's going to be really strange, I think. So let's see how that works. That's a complicated task. But look at that, that's beautiful. So apparently, since I simulated the data myself, I knew how to transform them, which is nice. But that's actually kind of nice sometimes. You can also do the opposite. I mean, you can transform Y instead. We could do it. So then we would do the square root. So let me try and do that. Here we are. So I can use the same, but then it's 0.5. That would be the square root, like this. I believe I'm going to get a strange error. Yes. The square root gave imaginary parts. Okay. Now let me just plot the data. Sometimes we get these strange error messages, and it's nice to be able to decipher them. Now, if you look at my Y data here, you see we have some negative values, so the square root is going to be a problem. So I could add 0.15. I mean, it's kind of ad hoc. I'm going to just take the absolute value. Then it cannot go wrong unless there's an exact 0 or something. No, that I don't know. It depends on how it's handled. Let's see. Let's do this. And yep, it seems to work now. Let's see the predictions. That's very nice. Basically the same, more or less. So again, that works. These simple transformations are kind of powerful. We can also do a little bit more, let's say a little bit more wild if we want. Let me show you a data set, which is a real data set. This is an NIR data set. So these are NIR spectra. And there's a little bit of, well, a little, oh, that's not the right one, sorry. Wait a minute, I need the Decatur one. It is the Decatur one.
Yeah, that was Decatur.
Ah, okay.
I know
Okay.
because I've been using that one this week.
Ah, okay, good. Okay, now you can see if you're into this kind of spectroscopy that there's a lot of scattering. Now we're going to talk about that a little bit later. for now, I just want to apply one of the tools that is sometimes used for removing or minimizing the influence of scattering. That's standard normal variate. And it does a semi-decent job here. This is not my point here, so that's why I'm not looking into that in more detail. I'm going to load my, if I can find them, my Y values, and I actually have 3 different ones, but I just want to try and predict the fat. This is meat, and I want to predict the fat content. I'm going to build a model with default cross-validation settings, a PLS model, and I'm going to go for a 3-component model, I think. It's not super important, but it's easier to see sort of the point that I want to make here. So now I'm going to look. Now this is a normal spectral PLS calibration, and you see here in the predictions we have the same kind of nonlinearity that we saw before, but it turns out that it's complicated. Well, at least I haven't been able to do a simple transformation of Y that will actually fix this. So what I'm going to do is that I'm going to do something else. I'm going to take X, but X now will have, in this particular case, 100 wavelengths. So now it's not just one variable, it's 100 wavelengths. And I'm going to take all of them and square them. So not only am I going to have my original variables, but also the squared ones. I'm actually also going to take interactions, x1 times x2, x1 times x3, etc. That means I'm going to do a kind of nasty nonlinear transformation of my data. Now, since I have 100 variables, these interaction terms can really go crazy. So what I'm going to do first is that I'm going to do a PCA and just work on the scores, because they will contain everything. PCA, if I take enough components, will contain all the systematic variations. So instead of 100 original variables, I will do this trick here on, say, 10 or some principal components. And I think I actually already did the PCA. Yes, okay, on just 6 components. So it's going to be much more, sort of much fewer interaction terms, etc. Okay, now if you go here, right-clicking on X, you can see there's a lot of nice things that we can do. We can do calibration transfer, we can reduce the data set, etc. But there's also something called polynomials and cross terms. And here I can do exactly the kind of transformations that I mentioned before. So the squares are turned on. So instead of just having my 6 scores, I'm now also going to have 6 squares. And then I want the cross terms, this one. So now instead of just having 6 variables here, I now have, let's see how many it ends up being, 27. That's a nonlinear version of my spectral data set. So now I'm basically just going to do the same thing again. And let's see. I guess the depressing thing is that it's not going to look nice at all. But wait a minute. Because I introduced a lot of different nonlinear transformations, and not all of them are necessarily useful. Maybe most of them are actually the opposite. So I'm making my problem less well specified. So what I'm going to do when I do this trick is that I'm going to do a variable selection. And we have other webinars about variable selection, I think. So I'm not going to go into detail with that. I'm just going to run one particular instance of variable selection, one called IPLS. And in reality, this is really just a forward selection. I'm selecting variables one at a time. That helps me improve the model. And let's see, hopefully, if I'm lucky.
Yeah, it won't take 5 minutes. Yeah.
No, this window is always depressing, because it kind of tells you how long is it going to take if I have to go on to the very end. But most of the time we don't have to go on to the very end, so you shouldn't be too depressed. If it says days or weeks, you might actually be depressed because then it's probably going to take a fair bit. But I mean, that's all depends on the size of your data and the machine. But anyway, now this is kind of, I realized that this is a little hard to follow, but we're basically just doing the same as we did before univariately, but now we're doing it on a set of variables. And I hope you will see that that actually helps improving the model. And one of the really nice things about doing this is that we could also have gone for a neural network or support vector machines and stuff like that. And it would work, definitely, it works quite nicely. But those are extremely non-transparent. It's a black box. So you don't get an idea on why does the model work, how does the model work. You don't get any outlier diagnostics, etc. When we do this trick here and transform our data non-linearly, we actually have the opportunity to use a linear model like PLS, and therefore we can do all the standard things. We can do outlier detection, we can do contribution plots, and all these different things. And this is taking too long, so, but anyway. And actually, I remember, so, okay, a little story. The very first time I met Barry was in 1994 in August, and he was giving a talk on how to do these nonlinear transformations and using another variable selection technique called genetic algorithms for selecting the subset of these nonlinear transform data that would give a nice model, which was a very nice application, and it worked quite well.
In Iceland, was that?
That was in Iceland in August 94.
God, I wouldn't have been able to tell you what I was talking about. But...
No, but I remember it because you provoked people.
Okay.
Because genetic algorithms were kind of provocative to a true chemometrician at that time. There was a very protective environment about new stuff. So, yeah, it was funny. Okay,
Well,
now
how much longer are we going to wait for this, Rasmus?
about half an hour.
Oh, there we go.
Okay.
There we go. Yeah, I was hoping that it would be a little bit faster. Okay, I may have done something completely stupid, and then I do apologize. Let's see now. Ah, God damn it! I apologize. I'm doing SNV on my scores and mean censoring. Now the SNV was for the spectra. I used that when I did my PCA on my spectra, but I shouldn't do that here. I really do apologize about that. But anyway, let me just leave that running and we can continue. I'm going to rerun this because I did something stupid. I should auto scale, because imagine I have variables that are like 10 numbers are in the neighborhood of 10, and now I take the square, that would be in the neighborhood of 100. And of course, that would give me some strangely scaled data. So just as I explained before, we really have to auto scale the data. But while this is running, maybe Barry, you can talk a little bit about some other applications of preprocessing.
Sure, I can do that. I was going to talk a little bit about using orthogonalization filters. So let me grab the host privileges back, and I'll just take 5 minutes now and do that. Let me see, change my own role to presenter. Here we go. And now I'm going to share my screen. And there we go. All right. So the data set, actually, I need to share my whole thing. Just a second. Stop sharing. Share again. everything. There we go. So we used to give this talk at conferences for a while where we talked about orthogonalization filters in general. And there's a whole lot of them out there. And so I just wanted to put this table up to show that there are a lot of them available. There's three that I'm going to talk a little bit about right here, and that's orthogonal signal correction, external parameter orthogonalization, and generalized least squares weighting. And they all depend on you figuring out what you're going to call clutter. Well, what is clutter? Clutter is variation in your data that is not related to the property of interest. And so clutter makes variation of interest harder to model. In fact, clutter was originally defined for radar systems as extraneous signals on the face of the screen, so clutter is signal that you don't care about. And there are several ways to estimate clutter and clutter covariance. Sometimes it is if you have data with classes, and especially when you're doing classification problems, you usually don't care about how the data varies within classes. You usually care about separating classes, and so you care about between class variation. So within class variation can be clutter. Y gradient can be clutter. Basically, that's the weighted difference between samples with similar Y values. And if you think about that for a second, if you're trying to model a variable Y, if you have two samples that have the same Y value, but their spectra is different, well, that difference is clutter. It's variation in your spectra that isn't related to variation in the property of interest. And so that's one way to get clutter. You can get variation that's just orthogonal to Y in your modeling, and that's essentially what orthogonal signal correction does. Or you could have some other a priori information about variance that you expect to see in your data that you want to get rid of. And so there's lots of ways to get clutter. Well, and then there's several kinds of filters that you can use that with. And one of them is external parameter orthogonalization, or EPO. And what you do is you build a PCA model of the clutter and then orthogonalize your data against the principal components in that clutter model. So basically, you deflate your data set using the factors in the clutter. And there you have to choose the number. How many PCs are you going to use out of your clutter model? That's a hard filter because the clutter dimensions are completely removed from your data set. And there's also one of the things that I mentioned, I think some of you probably saw what I posted on LinkedIn this week about generalized least squares weighting. That is a downweight by the inverse square root of the clutter covariance. And it can be tuned, so it's a little more complicated than just that square root. You can adjust how aggressive it is. And that's a soft filter because with GLSW, your clutter dimensions are only shrunk. They're not completely removed. And then there's orthogonal signal correction, or OSC. And in OSC, your data is completely orthogonalized against Y. And that is, you figure out what component has the maximum variation in X that is orthogonal to Y and remove that. And that's pretty much all I'm going to say about OSC here. But I have a little example for you. And in MATLAB, in the demo data here, there's one that's called olive oil. And if I load up the olive oil data, that's right there. And I'm going to take the calibration olive oil data and put it into PCA. And this is FTIR spectra of olive oil, corn margarine, corn oil, and safflower oil. And it's a data set that was collected by Don Dahlberg. But let's just do a simple PCA of this. And actually, I'll show you very quickly the data first. Let's just plot it. So here's the data. We're using the fingerprint region in the FTIR and this little vinyl stretch over here at 3,000 wave numbers. If I look at the data, all of the data looks like that. If I look at the classes in the data set, then you can actually see that different oils in here separate just slightly from each other in the raw data. Okay, so that's our raw data. Now let's make a simple PCA model of this. And I'm going to go ahead and show the scores for that. And when I do that, and this is just simple PCA on the raw or just simply mean-centered data, I can put confidence ellipses around my groups and show you then that I have them there, put the legend on so you can see what's what. So corn margarine, corn oils here, olive oils there, safflower oil. Well, if I now go ahead and define my clutter, click the clutter button, and say that if you look in the details here, what we're actually going to use is X block classes. That would be automatic, but I'll select it just to show what it's doing. We could do EPO here and remove one component out of this and say, okay. And so now I've got my EPO filter and then mean centering. Go ahead and remake my model. And you'll see that it shrank the variation in the classes because that was the clutter model. The clutter model was, I'm going to take the variation in the classes, model that, and then orthogonalize the data set against that, get rid of that variation in it. And you can try that yourself. Also, I could switch the clutter here to GLSW instead and say OK and try that. And GLS really works like gangbusters on this data set. And I'll want to get back here to Rasmus. But you see that here are within class variation got very small compared to the between class variation. And that's all because of how I defined the clutter filter. I designed that filter to remove within class variation. Okay, so Rasmus, you ready to go again?
Barry, before you move on, we did have a question. What are the GLSW default settings, and when would you ignore mean centering?
Oh man, the ignore mean centering, that's one to go to the wiki for. The default parameters, that's one that you want to try basically is this declutter threshold. The more you move the bar to the right, the more aggressive the filter is going to be. And so usually that's a little bit of trial and error. Again, you'd have to go look at the math of the filter to see what this number here actually means in the formulation of that. So that's a little beyond the scope of this. But that's the basic thing is you typically have to play with this a little bit. You can, if you make it too aggressive, you'll start taking out variation that actually separates the classes here and it'll all collapse. And so that's a matter of investigating the parameters. Okay, so I'm going to take it back to Rasmus, if that's okay with Rasmus.
Oh, it is. Yes.
It is. Okay.
You allow me?
And so just a second, I have to scroll
Yeah,
down and find you. We got quite a few people here today, which is nice. And if your name began with A, it would make it easier.
I'm sorry. Next time. Yeah.
Yeah. So I'm assigning.
A Rasmus Bro.
Yeah, just a second. Okay. So it should be you now.
Perfect. We got it. And in the meantime, I messed up. I'm sorry. We'll get back to that hopefully if I did something stupid. But anyway, for now, you can trust me that it actually gives really nice and linearized predictions. I just messed up with the variable selection while Barry was talking. I want to show you a few more things. And one thing is I want to show you something about baselining. There's a number of tools for baselining. And I'm going to use this Raman dataset. So these are Raman spectra. And we have a lot of fluorescence. So sort of the soft big hills here, that's fluorescence that you really don't want to have in your model. It's the peaks that are interesting. And right now the baseline or the fluorescence is sort of the major variation. Now, if you look here, there's a number of different tools that you can use for baselining. And they extend from very simple, just fit a polynomial to each line. So for example, you could fit a straight line to each of them, which doesn't really remove the baseline, but you can also try maybe a higher order polynomial. And it'll actually, I think a third order polynomial will actually do a fairly decent job, surprisingly well. But some of the other tools will allow you to deselect the areas where you have peaks. So we estimate the baseline based on only areas where we have baseline. And then all the way to some very fancy methods that are kind of hippie-like, not assuming any particular shape. So you can accommodate to baselines of sort of arbitrary shape, and you can specify to what extent there should be flexibility. And you see here that I took one of these and just used the default settings, and it does a pretty good job at removing the baselines. So lots of different tools for baselining that we could talk about, but we will not. I would like to load a, let's see if I have a spectral data set. Was the, wait a minute. No, just a minute. Let me just check. Here we are. Okay. So I would like to show you, some of the tools we have for scatter correction as a last thing before we're done. Where did my data go? I have too many MATLABs open. Apologies. So this is a spectral dataset that was generated basically to create as much scatter as possible. And it was done by Harold Martens, actually in our lab here in Copenhagen many years ago, when he was working in our lab. And it's basically just 5 types of samples, so 5 different samples, but with lots of powder and lots of scattering, so they look very noisy. And what we can do, for example, is that we can do one of the standard approaches would be the multiplicative signal correction. And it does kind of a nice job. There's a secret sort of a way of using MSC. You can apply it twice, not thrice, but twice. And sometimes that helps, which is really weird. It's a trick of Willem Wendig. And in this particular case, it actually does improve quite a bit. We can see now the 5 different types of samples. But when Harold Martens made this data set, he actually had developed a method called, where are we? Okay, slowly. Called extended multiplicative scatter correction, which uses a little bit more of the theory behind scattering to better model the scattering. And what you will see is that for this particular data set, it really does a wonderful job of getting rid of the scattering. It's not always that effective, but if you have huge amounts of scattering, this EMSC can be a useful tool. But just as an inspiration, I want to show you sort of an alternative. Let me try and do something here. Let me do the MSC, and then I will actually do a derivative. So I'm going to do a Savitsky-Goulet derivative, second derivative. That's also one of the standard tools. And I think I will also try, why not, a little bit of normalization with the area. And look at that. So even if you don't have access to EMSC, if you play around with the pre-processing, you may be able to reach something. If you build a quantitative PLS model on this, it's going to give you perfect predictions because we really have removed all the scattering. So if you're a little creative with your pre-processing, you may be able to achieve quite spectacular things. Okay. The very last thing I want to mention, and I'm just going to mention it, this is that we can also handle fluorescence data. And I'm not going to talk much about this. This is actually what I've been doing most of my life, so I could easily talk a day or two about that. But there is a very nice tool for handling excitation emission matrices, handling blank subtraction, dealing with Rayleigh and Raman scattering, and also handling sort of the typical artifacts that we can see in fluorescence data. It's a very nice tool, a generic tool for pre-processing fluorescence data. Okay. This was basically what I planned to talk about. If there's any questions, I'll be happy to answer them.
Well, there's been actually a lot of questions going by in the chat that have mostly been answered by the Eigen guys as they've gone. Some of them are pretty specific and complex and deserve some follow-up. So I'm not going to give them to you, Rasmus, because we'd be here all day.
Let me just do one thing. Let me prove my point, hopefully. Let's see. God damn it, it's not as nice as it should have been. But this is the linearized predictions that I did. Yeah. Damn. I was expecting something better. A little more work and we could get much nicer predictions, but we did remove most of the nonlinearity.
There was a question about mass spec data and tools used there. We do have some tools there. For one thing, the Poisson and Pareto are used a lot to normalize mass spectra and bring out especially the smaller features. Another thing that's used, which I won't show, but there's actually a tool in there specifically to upweight higher masses relative to lower masses. And I'm trying to remember what it's called. Can you bring up the pre-processing window?
Is it this? No, it's the log decay scaling.
It is exponential, I think, is log decay scaling. So that's one that is used to upweight higher masses. It basically applies a scaling to the mass axis so that higher masses are upweighted because higher mass fragments are always in lower abundance than lower mass fragments in mass spec. So between those and the log decay scaling and Poisson, those are usually pretty effective in mass spec. So don't have an example of that now. Okay, and here's a good question. Besides visual improvements, how have you used model statistics to determine the success of pre-processing? Well, especially in either classification problems or regression problems, usually you have some objective measure there. In regression, it's what your root mean square error cross validation or error prediction on a separate test set is. So you can survey your pre-processing methods against those and see what's working. in classification problems, it's the same thing, only successful classification rate. And so those are usually your determining thing. It's a little more difficult. Sometimes we use various types of scaling when we're going to do curve resolution, and there, in order to tease out smaller features, there it's a little harder to put an objective measure on what's working better. It's usually a little bit more a matter of taste. There's a question here. This is good for you, Rasmus. Do the mentioned preprocessing tools apply to three-way data like EEMs?
Yeah, let me show you. So normally we have this long list, but if you have a fluorescence data set, which is actually what is called a three-way data set, if you load the if you sort of look at what preprocessing you can do, you can see that it's sort of limited. So not all of them are implemented for three-way data. Not all of them are actually useful for three-way data.
But there are some that are.
Oh yes, there's a bunch.
Oh, yeah.
And can I just mention? I don't think you mentioned it, Barry, but there's this model optimizer, which is often used for choosing preprocessing. It's an extremely efficient tool for comparing tons of different sort of settings. That could be preprocessing and other things. It's a very, very useful tool. So if you don't know about that, I urge you to look into it. It's very powerful for building calibration models, systematically investigating sort of the whole solution space.
Okay.
Yeah, it's the model optimizer. Do we have a webinar on this? I guess we do.
Yes, we do. We do have a webinar on model optimizer.
Okay, so just Google Eigenvector model optimizer. Well, I can Google model optimizer Eigenvector. Webinar.
Okay, I'm about ready to claim the host privileges back from you here, Rasmus.
Yeah, sorry. Okay.
Okay. Yeah.
If you Google that, you'll get it.
Yeah, actually, I'll show you where it is. Just a second. I'll do that right
Scott
now.
Scott just added the link to the chat.
Ah, see.
So, okay. Let me see. I want to share my screen and go back to just the presentation. So, thanks for joining us today. I knew this would go a little bit long because there's really just so much to say. And I think this is what I said previously is it wouldn't be everything that there is to say about preprocessing. It would just be as much as we could get into in an hour. And Rasmus hit some things that we don't focus on all that often. And so I think that was really kind of nice. It was a little different view on it. So I want to mention that the webinar series, if you go to our website and look under resources, there's the webinar series. So there's a whole bunch of them that you might look at that to get started and kind of up to the point where we are now. There's one on just flat getting started about importing data, PCA, recent one on PLS regression that was very good on that, one about cross validation, and 14 more. So Scott pointed to the one on the model optimizer. And we also have a lot of recorded courses under our training menu, and in particular, our advanced spectral preprocessing course is there. It runs 7 hours and goes into greater depth and with more examples on a lot of things that we've talked about today and more. And do we see any other questions here, guys like Bob, that we ought to answer before going?
I think we're caught up.
Okay. All right. Well, in that case, I'm going to just thank everybody for attending and sign out.
Okay. Thank you, everyone.
Yeah, thank you, Rasmus. That was fun.
Yeah, it was. Thanks.
Thanks, Rasmus.
Thanks.